Hi everyone, I'm Shreya. I'm a second year master's student at Stanford in the program called Symbolic Systems. It's essentially at the intersection of CS and cognitive science. I did my undergrad in India from Delhi Technological University, where majored in CS, where I did a lot of like machine learning and various applications of machine learning in different domains. And I'm very excited to um, teach here and discuss with you about deep learning, machine learning, coding in deep learning, etc. So far we have already talked about gradient descent, what gradient descent is, how do you calculate gradient descent, what you have a loss, which is based on how off your predictions were as compared to the expected values, and how now you go on to update your parameters by which you calculated your expected values. And those parameters were essentially weights and biases. Now we want to update those weights and biases, and that's where gradient descent we discussed comes into picture. Now we want to go on actually do it. But we saw before that these equations can be pretty complex to implement. And it's very hard to do them by hand every time, all the time, especially as your network currently, like for example, in ChatGPT like devices, like the network can be pretty huge. So it can be pretty hard to do it by hand. So this is where autograd comes into picture. Now, what is autograd? Autograd is this package in Python that automatically computes the gradients of mathematical functions like we saw before. Now it does it by building a computational graph of the operations performed on the input variables, which in our case can be uh, calculating the gradients, for example. Um, and then it applies the chain rule to calculate the gradients of the output with respect to the inputs. Now, how it can be useful for our use case is that it can help us with calculating gradients. With autograd, the user like us, we would not need to manually derive and implement gradients, which can be very time consuming. Instead, autograd will derive and implement these gradients automatically and very efficiently, so that we could focus more on like design of our models instead. This autograd is a part of PyTorch, which is the library that we're essentially going to be using for our deep learning frameworks. And it is very widely used in the research community as well to develop machine learning models. Now let's look at a code to understand using how can we go about using autograd for model building. So we now this code will use this class called simple graph that we have defined. This will implement a simple computational graph. This graph has an initializer method that initializes the graph's parameters, a forward layer that will implement a forward pass that is calculating the output by the model, and an SQ loss or a squared loss method that will calculate the L2 loss or the squared loss between the prediction and the actual values. To go further, now that we have a high level idea of what the simple graph essentially kind of looks like, let's look into it further. Now this initializer, in the initializer, we define the parameters as PyTorch tensors. And this is the thing that does the magic. This is requires grads is equal to true. Now this indicates to PyTorch's autograd engine that we want to track the gradients with respect to these tensors during backpropagation when we want to actually go on update the weights and biases. Now, in the forward method, we calculate the model's predictions by performing the TANH activation that we talked about on the dot product of our input with the weights and adding biases to it to calculate our prediction. This is simply y is equal to mx plus c, the equation of a line that we have discussed. Now, in the final method that we have, in the SQ loss method, we calculate the L2 loss between the predicted and the actual values. What is the L2 loss? L2 is just symbolizes that it's going to be a squared loss between the expected values and the values that our model or our simple graph is going to predict. And sorry, now this function will calculate the gradients with respect to the inputs and weights. So what this loss, actually not right now, but maybe later, but right now what we're doing essentially is we're calculating the loss, and how we define this loss is, so how much of the data are we losing? Essentially, when we have this model that we have defined, and we are making a prediction from this model, how off is our prediction from the values that we wanted to get at? That's kind of how we learn most things in life. We make some inference, just like a random inference, and then somebody gives us a feedback that, hey, this was where you wanted to get at, and this is where you are. So you want to see how far off you are so that you could like take steps to actually bridge that gap, right? So this is how we define our loss. We have our true values and we have our prediction values, and we see how far off they are. The reason that we are squaring them is because we want, it helps us in the process when we want to differentiate this loss with respect to different values. It is helpful then, and we also want to penalize this loss. That is, we want the larger values or the more incorrect values to be penalized more, so that they could like move quicker towards our expected values. So this is what your L2 loss is. L2, this N1, L1 loss as well, which is simply your Y true minus Y prediction. L2 is when you square things up. Finally, we can add event, we can run this, and we have some initial weights that we can define. We can define some initial biases, and we can calculate for different values of x's and y's what x's and y's sorry, what your prediction and L2 losses can be. Yeah, happy to answer questions. Okay. How do you stop this?